the homeworks. Chapter 6 you have, right? So, okay, I'm just writing down the things that you have, because I didn't cover all of the material, but some of the material I have covered from all the chapters. Basically, I didn't cover young tableau, essentially, right? So, from 7th chapter, chapter 7, you have to do 7.1, 7.1, 2, 3, and 6. That's 7th chapter. Chapter 8, you have 8.1, 2, 3, 4, 5, 6. Because these are all, they don't involve young tableaus. All of these things do not involve young tableau. And from chapter 9, there are no problems. So chapter 10, there is only one problem, and that is 10.1, which was a simple problem about the definition of the EIJ, that matrix EIJ. Okay. And instead of that, of the young tableau, what we have been doing is using the highest weight, and So I think I already gave you some problems there, but let me just repeat that again. So the first problem is construct all the weights of the irreducible representation labeled by the highest weight state, for SU3. So the highest weight states are 1, 0, which we have again done it, but let's see. So this one, A, B, 2, 0, and 3, 0. So the notation here is this is the weights which we label there. So these are the highest weights with the eigenvalues. These are the eigenvalues of H1 and H2. Not Y, H1 and H2. So this is eigenvalue H1, highest weight has eigenvalue 1 with respect to H1 and 0 with respect to H2, and so on. So that's the notation here. This we have gone through, I think, but in particular, you need to construct the representation, you find the multiplicities of the states. Multiplicities of different states here. Right. Remember, I think I gave you one example where there were two ways of reaching. By applying lowering operators, you can arrive at the same state in two different ways. But those two, so a priori you would say there are two linearly independent states. But it turns out that in one of the examples, in this example, there was one combination which was not, they were linearly dependent. So they were not two independent states. No? So in that case, the multiplicity is only 1, not 2. No? So that analysis. Okay, and then finally some tensor products. Decompose. So this is the second question. Decompose the following tensor products into irreducible representation. Irreducible representations. Okay. So these examples, so the questions are, again, these examples we went through in the class, but maybe not too much in detail. So the notation is the same. This is the highest weight, the same notation. 2, 1, 0 with 0, 1, and 3. I think I went through all of these examples, but 1, 0 times 1, 0. For this, sorry, one more thing. Just one more I can put here. A, B, C, let's say D, 1, 1. This is, of course, is a joint representation. But the reason is that you can come to the answers very quickly by looking at the. So the procedure, I think, very quickly you can do the following. What did we do? We looked at the highest possible weight, right? That's like a SU2 case, right? If you have a J1 and J2, the highest tensor product of these two, the highest eigenvalue will be J1 plus J2. So you know for sure there is a spin J1 plus J2 representation, right? You remove that, then you ask what is the next highest weight state, right? And so on. You can, this way you deduce all of it. So the idea is exactly the same. You go, you look at the highest possible weight here, right? Then look at this list, if there is anything here. So that goes out, right? Then look at the remaining ones, and you should be able to get the answers to this question. Just basically using these results that you already have. You know the dimensions of each of this representation from this exercise, because you know the multiplicities and you know all the weights. Then you know the dimensions of this. So you know that that many states will you have to take out once you go to the highest weight state there, right? Then you look at the remaining ones. So that's the procedure. Yeah. So these are also I think physically the most useful tensor products that you will come across. This is a fundamental times fundamental, fundamental times anti-fundamental, and the fundamental cube, which is gives you the baryons. No? So these are the interesting ones also. Okay, so that's it for this. I don't know, will it be too much until this Friday? Because Friday means it's 2 days.
Yeah.
It's too much. If it is too much, then maybe we can split into two parts. Huh?
No, we can.
Okay.
No,
Try as much as we can.
We can tell tomorrow.
We can do it tomorrow.
We can tell tomorrow if it's too much or not.
Yeah, okay, fine. Yeah.
Now I wanted to ask you, in the case of P0, what is the action of x minus alpha 2 on the state?
X minus?
Alpha 2.
X minus alpha 2 will be 0, of course, right? Immediately when you apply on that highest weight state. Because from the H2 point of view, this is spin 0, right? H2, the SU2 corresponding to the X alpha 2, right? Because remember, they formed the two SU2 subalgebras, X alpha 1, plus minus, X plus minus alpha 1 and H1. They formed one SU2, and another one was X plus minus alpha 2, H2. This formed the second SU2 algebra, right? There's another third one which is alpha 3 and H3 and so on. But this is enough because alpha 3 I can obtain from commutational relations of these two. So you don't need to consider alpha 3. Right? So this is enough. And these eigenvalues are telling you these are highest weights. So this tells you that it is spin 0 with respect to the second SU2. So the lowering and raising operators, everything annihilates that state. Both plus alpha 2 and minus alpha 2 annihilates it. But not, that is the starting point. But you see, so just to again, so what was the situation? I have 1, 0. It is true that alpha 2 will annihilate, minus alpha 2 will annihilate it. So there will be nothing coming in this direction, right? This was the minus alpha 2 direction, that it will annihilate it. So there is nothing there, this is not there. But with respect to the first SU2, it is spin half, right? Because remember, there's a doubling here. This is it's a 2 times J, right? Because our normalization was just sigma 3 rather than sigma 3 by 2. No? So there's spin half representation with respect to this SU2. So for sure there will be one X minus alpha 1 acting here. Okay, you'll get something. But not that something, there this can act. Okay, this can act because if you look at this carries also an eigenvalue with respect to H2, right? X alpha 1 carries an eigenvalue with respect to H2 also, right? So this state will have a non-zero H2. Okay, in that case, of course, you can apply X minus alpha 2 also, right? But not the first step. The first step, this is spin 0, so no. So there is no. This will annihilate it.
Do I gain anything by considering 0, 3 instead of 3, 0?
No, it will be the equivalent. It's just a complex conjugate representation.
Okay.
So 0, 3 will be just the complex conjugate of that representation. It's like for the fundamental, for the 3, you had this this kind of a triangle, right? Here were the weights of the 3. 3 bar is just minus. The same way for the 3, 0 also. 3, 0, I think I did work it out, was a 10-dimensional representation, but that was not symmetric under the the weights going to minus weights. No? So under the complex conjugation, it just becomes the weights go to minus weights. So it'll be different, 10 bar.
So if I wanted a higher representation of SU3, I would consider 4,0, for example,
Yeah.
and apply.
Yeah.
Is there
It
a
starts
easier
at-
way to obtain all the different dimensions of the representations?
This formula I gave you, the formula, yeah?
Yes.
Remember that formula was, for at least for SU3, the formula was N1 plus 1, these numbers, N1 and N2. No? N1 plus 1 times N2 plus 1 times N1 plus N2 plus 2, correct? Divided by factorial of 2, which is 2. Yeah, this was the formula for the dimension. So in fact, you could check that. You could check, I mean, if you're not getting the multiplicities right, you would not agree with that result, right? So that is another way to check it. So this is the dimension of irreducible representation labeled by N1 and 2. I know, I did this, I started on. Now it's become a habit. The moment I enter, I switch it on.
And you can also get from the Young tableau, right?
Young tableau, actually the relation between N1, N2 and Young tableau, I mean, I didn't discuss Young tableau, but if some of you probably are familiar with Young tableau already, it's just that if you take some Young tableau with certain number of boxes, roughly speaking, although I didn't discuss anything, but this Young tableau, etc., are basically saying that these horizontal lines, so let's suppose here there are five indices. I mean, so in this you have TI, I1 up to I5. So there are 5. So for each index you put a box. And so what we are doing here is that this notation essentially means that horizontal lines, these are symmetrized, totally symmetrized, and the vertical lines are totally anti-symmetrized. So it's clear that for SU3, you have at these indices, each of them transform in the fundamental representation, right? So for SU3, fundamental representation is three-dimensional, right? So if I put something which is of this type, let's say I look at the three of them, I1, I2, I3. Okay, so I look at this diagram. What it means is total anti-symmetrization. But if it's total anti-symmetrization, it's a singlet, right? Because the only thing which is totally anti-symmetric is epsilon I1, I2, I3, the Levi-Civita symbol, right? So this is one-dimensional. That's the only possibility. So this thing will be a singlet. Okay. So therefore, you don't need to. So for SU3, what I'm saying is that the maximum you need to do is to have 2 rows. 2 rows. You don't need the third, because if I have a third row here, I can just remove that, because that's going to be a singlet. Epsilon ijk is going to be proportional to epsilon ijk. No? So that part I can just remove that. Okay. So you can just stay with 2 rows. Okay. So in general, the number. So and there's a rule that there's a convention that the upper row should have minimum the same as the lower row boxes. So it cannot be that that is not to overcount. You don't want to overcount. You don't put diagrams like that. Okay, this is not allowed, but this is allowed, or even the equal numbers are allowed. But okay, this is also allowed, but not this. So these two are allowed. So anyway, there's a rule that as you go down in the vertical line, the number of boxes cannot increase the preceding ones. So it can only decrease or can be stay equal, but not increase. Then the translation between this language and that language is this is say N2. The number of boxes is N2 here, And the number of boxes here is n1 plus n2. Okay. So that's a simple translation of the language that we are using, the highest weight language, and the Young tableau. And that's okay. Young tableau is very useful to construct these kinds of decompositions. That's very useful because you just start taking these different representations, different Young tableaus for each of them, and start combining them. And there are rules, there are recipes. How you should distribute these boxes and so on. But the reason why I didn't go through that is that that's just a recipe. One cannot prove those things unless one knows a lot about the permutation groups. And since in this course we are not covering the permutation groups, are pretty complicated groups for a large number of indices, it starts becoming extremely complicated. So that's why I didn't go through that.
In some undergraduate courses, they also teach Young tableau to decompose the. If you have two particles and you want to know the angular momentum states of the product system.
Yeah.
Then you can also do it.
That's right. Yeah.
So in some undergraduate you do teach.
Yeah.
But it is used for all the recipe.
SU2, because that is SO3 or SU2. That's much easier because you see the number of for SU2 even this is trivial, right? Because this the node SU2 will be this will be doublet, right? If it was SU2. So each of them is only two-dimensional, fundamental and two-dimensional. So the only antisymmetric thing is epsilon ij. So you can get rid of that. So for SU2, everything is just horizontal boxes, horizontal one row. No? So that's why it becomes even simpler to use Young tableau. But SU3 and higher things starts becoming more complicated.
But you do understand that becomes very handy.
It's very useful to get quick results, quick answers, but you have to follow the recipe. You have to follow the recipe, and there is to prove that recipe gives the correct answer. That requires some knowledge of permutation group.
Kind of like Feynman diagram.
Sorry?
Kind of like Feynman diagram. Feynman diagram can give you the result. You can do it without Feynman diagram. Something like that. You can say.
Yeah, but Feynman diagram, you understand the logic of that, right?
Yeah,
The point is that the problem of the Young tableau is to understand the logic. You need to learn something about permutation groups. Whereas the basic logic in this way of doing it, where you just start taking the highest weight, that representation out, look at the remaining ones. That is the basic concept involved there. No? Okay. I don't know. Maybe I don't think I will get any time, but because I have only now how many? Next week 3 and tomorrow, so 4 lectures. But if I do find some time, maybe the last lecture I could say something about the Young tableau. But I don't think I will find time. Actually, I will have shortage of time. Actually. Okay. Now, so can I erase this now? Okay. Okay, so now we go to the more kind of formal. We already discussed the ideals, and now then we also discussed chapter 10, so 11. Yeah, that's an very important concept. The Cartan-Killing form. So what is the idea? So we have the Lie algebra, some Lie algebra. It's a vector space, right? And it's a vector space, and it has the commutation relations. These are the two main properties of the Lie algebra. But we would like to have some kind of a notion of a metric distance, no? That we have not introduced yet. No? But also that whatever notion you put, whatever kind of concept you put for the metric, it should have some nice properties. Not just any arbitrary metric. So that was given by Cartan-Killing. That's what is given by the Cartan-Killing form. And the way you define it is, let's suppose x and y are elements of G. So I want to define some kind of a notion of inner product of X between X and Y. Right? That's what is metric, inner product between X and Y. And that is defined in the following way. Take the adjoint representation, so in the add of X and add of Y. So each of them will have the same dimension as the Lie algebra, right? I mean, if Lie algebra has dimension, say n, if this Lie algebra has dimension n, then this will be n by n matrices, right? Each of them adjoint will be the same dimensional as a G. And that is why. Why is that so? Because add X maps G to G. A linear map is a linear map. Linear map. And any linear map you can write it as a matrix. Now add this G is an n-dimensional vector space. So this is mapping n-dimensional to n-dimension in a linear way, right? So therefore this I can always think of as an n by n matrix. And very explicitly what you do is that just choose a basis for this, right? And then see how the basis transforms, right? And then from that you can deduce the explicit matrix form. But of course explicit matrix form depends on the choice of basis. But nevertheless, okay, that is sufficient to show that this can be thought of as an n by n matrix. Then I can take the product of these two n by n matrices and take the trace. Okay, this is what is called this is the Kaplan-Killing form, which is denoted by, at least in these notes, lecture notes, we are calling it BXY. I would have preferred to call GXY, G being the metric, but anyway, BXY. So you see, immediately you see one thing, that this is symmetric in X and Y, as the inner product should be, right? Because this is, I mean, if you exchange X and Y, this is add Y, add X, but this is, trace is always cyclic, so you can move it back again, right? So BXY is the same as BYX. So it is symmetric. So this is the definition. This is the definition of the metric, Kaplan-Killing form. Now, okay, we can very explicitly write it in terms of, write this quantity in terms of the structure constants of the Lie algebra. That is clear because after all, adjoint, these matrices themselves can be written in terms of structure constants.
Can you say that the Kaplan-Killing form is an inner product?
Sorry?
Can you say that the Kaplan-Killing form is an inner product?
Yeah, I think so.
So the inner product says that if X and Y are the same, then the inner product should be positive definite. So how can we see that?
No. So inner product not in that sense at the moment. Okay, it could be even negative. Could be even negative. Yeah.
So it is not positive definite.
Not at this stage. Of course, yeah. If it is negative, you could always multiply by I. In the complex space, it will be. I mean, it's not. It will be indefinite in the complex space. But in the actual Lie algebra, it will be either all positive. I mean, say let's take SU2 or SU3, depending on what conventions you use. It will be either completely positive or completely negative.
It's not actually an inner product. It doesn't satisfy all of the things of inner product, but it is kind of it turns the Lie algebra into a matrix. You can say that, or not?
I mean,
It's a metric, right?
It's a metric. Yeah, but when you a metric, you always you can define the inner product, right?
But it's not positive definite.
Yeah, that is fine.
Okay.
Yeah, anytime you have a metric, you can always. I mean, so for example, let's say choose a basis. So let's say Ti are the basis. I going from 1 to n. Then I can define a Bij, which is simply the trace of add Ti with add Tj. No. Then any x which is say xi Ti and y as yj Tj. Then this Bxy is simply Bij xi yj, right? So it's just this provides a metric, right? Of course, I mean it need not be, but for it to be metric, it should be non-degenerate. Okay. In general, we are not guaranteed at this stage.
Non-degenerate means that the determinant should not be 0.
Exactly. So inverse must exist. That the determinant should not be 0. So that is not guaranteed. In fact, in many of the algebras, this will be in fact degenerate. Okay, and what we will be doing in the rest of the course will be to restrict ourselves to those algebras where this is non-degenerate. Okay.
So it also means that if the canonical form is 0 for some x and y, then x and y need not be 0.
Yeah. So yeah, exactly. So what I'm saying in general, B could be degenerate. B could be degenerate, which in the language, once I choose a basis, that is the same as saying the matrix. Matrix Bij. Matrix defined by this Bij. B11, B12, etc. all the way with these Bij's being the entries. This matrix has determinant equal to 0. Right? So this matrix, so bit of this matrix equal to 0. That is what will be degenerate. Or in a more invariant way, without choosing any basis, one can say equivalently that if it is degenerate, that means there exists some x such that b of xy is equal to 0 for all y belonging to G. That's an equivalent way of saying it.
All of y.
For all y.
Why are you defining it with the adjoint representation?
Yeah, I mean, okay, that was the original definition. Now, in general, it is not obvious that if I choose another representation, right, that the answer will be proportional to the original one. No? But again, in the class of models that we'll be talking about, which is the class of algebras, which is simple algebras. Okay? Simple algebras, it turns out, it doesn't matter which irreducible representation you use. They are all proportional to each other. No?
It might be because if we are studying any arbitrary algebra, we don't have to find any representation for that. We have already a representation that joint.
Exactly. Yeah. That so it's this is guaranteed, right? I mean, okay, for the matrix groups that we have looked at, there is a defining representation. That already gives a fundamental representation, right? But in a more abstract way, if somebody gives you a Lie algebra which is not referring to any matrices and so on, what is given to you is the adjoint representation, right? Because the commutation relations are given, and that is all that is required for the adjoint representation. No. So adjoint representation is always there, whether it's coming from a matrix algebra or some very abstractly defined algebra. No. So, but yeah, indeed, for SU2 and SU3, etc., we had the matrices. So SU2, I could use a two-dimensional representation here, right, which is the fundamental representation. You will get an answer which will be proportional to this answer.
So can the Cartan-Killing form be in general be a complex number?
Can
this be xy can be a complex number?
xy, bxy, I mean, that depends on what you are doing. I mean, if, as we said, we always working with the complexification of the Lie algebras. So in general, they will be complex numbers, right?
Okay, so if they are complex numbers, then is it necessary that if you switch x and y, then it should be equal to, or it should be equal to the complex number?
No, this is symmetry is just coming from the cyclicity. Cyclicity, so that's always there. But you see, at the end of the day, even though in the intermediate steps we complexify the Lie algebra, but finally we'll go to some real subspace. No? For example, for SU2, we just impose hermiticity condition, no? And then you come down to the real subspace. Okay, so this is quite an important thing. Now, why is it so? I mean, after all, you could have defined any symmetric form between the two in the Lie algebra, right? Why this particular? What is nice about it? And that is given. Before that. So let me just explicitly write down in terms of structure constants this matrices. Although this can be left as an exercise, but okay. So let's say, what in fact I wrote here. Let's say, so let's say So I've chosen a basis, right? Ti, I've chosen a basis. And let's suppose Ti, well, the commutational relation of Ti, Tj will be given in terms of some structure constants, right? I, J, K, Tk, right? That will be some for some numbers here. Right? Of course, it's antisymmetric in I and J. So what is add x? So one could do it the following way. So we want to look at the action of add x, add y on the basis, right? After all, this is an n by n matrix, right? So this is before taking the trace. Okay? It is acting on this basis, so TIs. So let's apply this on this basis. Okay? And then to take the trace, I just take the diagonal components, right, from there. So let's apply add x, add y on, say, Ti. So then I do it step by step. So this is the same as add x, acting on so this is nothing else but the y, Ti. Add x is acting on now this. Right? But then I rewrite this using this expansion yj, tj. So this is the same as add x, acting on yj, and commutator of tj with ti. But that is nothing else but fji k tk. Yes? I mean, so just I use this expansion yj, tj, and then take the commutator of yj are numbers, so that doesn't enter in the commutation relation. Commutation of tj with ti is given from this formula here in terms of structure constants. Okay. Now these are all, of course, numbers, so I can take this out of this add x. Right? These are all numbers. So this is the same as yj, fji, k, and then I have to take the commutator of x with tk. And then again use this expansion. So write x as something else, let's say xl here. So then you get yj, xl, fjik, and then the commutator of tl with tk is flk, say n tl. So what it has done, this action add x, add y has taken ti to this combination. Now I want to take the trace. So I want to look at that component which gives you back again ti, right? Because trace is that diagonal components. That is that part of this object which takes ti to ti, right? And then sum over all I. That will be the trace, right? So that means I should look at the component here where m is equal to I. So that component, so when I take the trace of add x, add y, that is simply yj, xl, fjik, and fflk I, because I have to take the m equal to I term, because that will be the diagonal term, right? Right? Because I mean, so far this is telling me that this is an operator. So this is a matrix which takes operator which takes ti to this combination. But ultimately, I'm interested in taking the trace, right? So I have to look at the diagonal components for the trace, right? The diagonal component will be when m. Here's a summation. So all the m's are there, but I pick out only the I term because that's what's going to be the diagonal. So this is what the expression is. So therefore, by comparing this with this, so you see that this is nothing else but BJL, right? In this notation, BJL. So BJL, which is simply, quadratic in F, the structure constants. So that gives you immediately the metric. So it's very explicit. For example, for SU2, for SU2, this is nothing else but a suitable choice. This is nothing else but proportional to epsilon jik right? For SU2, for SU2, Fijk is basically epsilon ijk, depending on whether 2i or I think, let's say if I use the basis sigma I, okay, then there will be 2i, right? If I use half, then I think there is nothing here. If I use this basis, then it is simply I, epsilon ijk. So then I can multiply this here. So you see you get here epsilon ji k, epsilon lk I square is minus, right? And I have to sum over all the repeated indices. The fixed indices are j and l. These are the fixed indices. I have to sum over these two things. But that's the same as if I, well, this ki I can exchange. So it is ik. The minus sign goes out. And this just tells me this is equal to 2, right? 2 j delta j. So for SU2, for this choice of basis, it is plus 2. If you had chosen the anti-Hermitian basis, you put an I there, then basically the result will become, so if you put an I, sigma I by 2 as a basis, then it will become minus 2. Because there will be an I again in this, the structure constants. This I will not be there, right? So you'll get a minus sign. I mean, here initially you had a minus sign, which became plus by exchanging these two. But if the I was not there, initially you had a plus sign, but exchanging these indices, it will become minus. So that's SU2 was simple. Same thing you can try. You can also write. In principle, you can once you have the structure constants, you can immediately construct. Now there is an exercise 11.1. This is very important exercise, huh? So please do that. I mean, not for this Friday, but this you should really do this very carefully, because this result we'll keep using it in the later part of the course. Huh? The result, which was a statement that if I take the Kaplan sub-algebra H1, H2, then where H1 and H2 are elements of Kaplan sub-algebra, H1. I think I could just write it as some H and K, let's say. Not because H1 and H2 was one particular basis we had chosen, right? But in general, if I have H and K, two elements of the Kaplan sub-algebra, then the statement is that this is equal to sum over alpha H, alpha I H, alpha I K. Okay, where these are all the roots, summed over all roots. Alpha I belong to the roots. In the exercise 11.1, if you look at it, there is a factor of 2. Okay, but that is simply because here it's understood that you sum over only positive roots. Okay, but if you don't care about the positive and negative, this is sum over all roots. But we know already that for every positive root, there's a negative root, right? So this is the same. If it's a negative root, both of the signs become minus, so it gives you the same contribution. Minus times minus is plus, no? So therefore, it's the same as 2 times alpha I now belonging to positive roots. Alpha I H, alpha I K. Okay. So yeah, the discrepancy between the two and in this exercise, it is not clearly stated that the sum is over positive roots. Yeah? Okay, so if you have sum over all roots, it should be just 1, not 2. So this is an important exercise, and this we will be using again and again.
That's for SU3.
SU3. But I mean, this exercise, no, it doesn't have to be. You can prove it in general. Yeah. But okay, do it for, I mean, SU3. I mean, you can prove it in general. Okay. I mean,
how can we see that it's very positive?
Well, so just prove this formula. So don't prove this formula, that sum of all roots. So the main thing you have to assume is that Cartan subalgebra, you can find simultaneous eigenfunctions of this H and K, add H and add K. Because they commute anyway, so it's kind of believable that you can find simultaneous eigenfunctions. No?
And we are assuming it's true for any any Lie algebra. We don't have to assume that there are only two elements in the Cartan. The basis.
No.
They can if you get any two of those, and you will get
Yes. So the main assumption here is that you can simultaneously diagonalize this add H and add K. Add H and add K can be simultaneously diagonalized. So in other words, you can find the eigenfunction simultaneously diagonalized. This is the main thing. And the fact that H with K commutes, right? Because of the Cartan. These are the two facts which you need to use. It's not very difficult. I mean, you see, I just will give you a hint, because maybe without the hint, it may be a bit difficult to start the thinking about it. I mean, go through the similar procedure. No? So choose some. So let's suppose. So we can simultaneously diagonalize. So add H acting on add H. So H commuted with any element, say X alpha, is. I mean, I found the eigenfunctions. So it is some alpha H X alpha, right? So you put here several different alpha I. So alpha I H. So suppose I found. Of course, H with the Cartan subalgebra itself. I mean, H with any element, H with H prime, where H prime belongs to the Cartan subalgebra, that is 0. That is, of course. Now, try to choose a basis. I mean, instead of choosing this Ti basis, choose the basis to be, let us say, this part is a Cartan part, right? Suppose Cartan subspace is, say, R dimensional. No? R is a rank, that's R dimensional. So this, you first choose the R vectors, which are basis R vectors in the top R part. Then you choose all the guys all the X alphas, alpha I. So you have alpha 1, X alpha 2. So these are all the distinct roots, whatever the number of roots is, X alpha n. So choose this basis. Of course, at this point you don't know that for a given eigenvalue, I mean, that there is only one eigenfunction. There could be the multiplicities, no? It may not be one only. But so whatever the multiplicity is, that entire space here, all the vectors, all the guys which have the eigenvalue alpha 1. It may be more than 1. A priori we don't know. It will turn out that U is 1. For the class of algebras we'll be studying, there will be always 1, not more than 1. But for the moment you don't have to assume that. So whatever, and then in this basis, write what is add H and add K. So, write that, and then just use this formula for the B, add H and add K. So you have kind of, you don't need too much detail. Basically, you should be able to show that each of them is kind of block diagonals in these blocks. And then you can find the trace and show that this formula is correct. So if the multiplicity is more than 1, then you count it more than once. Suppose alpha 1 comes more than once. Then this is summed over all of them. So alpha 1 will be counted twice. Okay. If there were two different eigenfunctions, x and x prime, let's say, both had the eigenvalue alpha 1, and these were linearly independent. If it had happened, then you would count this, in this sum, you would count it twice. Okay. So it's just that. I mean,
and in the Cartan basis, the matrix of add of H and add of K is actually 0, so you don't have to include the contribution.
Precisely. Yeah. And the only contribution will come from the non-zero roots, which is already diagonal. So I mean, this matrix is basically block diagonal, right? All these matrices are block diagonal. So then they take the product of the matrices. So this formula is pretty easy to derive. But it is very powerful. I mean, you will see. We'll keep using this formula again and again. Okay. Yeah. So what is nice about this this definition? This definition is nice because, I mean, let's suppose there are some symmetries in the which acts on the Lie algebra. So some kind of automorphism, okay, which takes the Lie algebra to itself, right, and which preserves the computational relations. Yeah, that is what when you say automorphism of acting on something, on some kind of some entity. That entity is defined by certain properties, no? So when we say automorphism, which means that all those defining properties are maintained, no? That is what. So here the vector space structure and the defining properties are vector space structure and the computational relations. Okay. So some automorphism which preserves these two things. Vector space structure is just a matter of linearity. No, that is okay. The more important thing is to check the commutational relations. I mean, to ensure that the commutational relation is satisfied. So, so let's suppose there is an automorphism. So suppose there exists an automorphism. Let's call it phi, which maps phi from the Lie algebra to Lie algebra, and furthermore phi of x, phi of x, phi of y is the same as phi of x comma y. That is, so it preserves the algebra. It's an automorphism, so it's a one-to-one map. It's a one-to-one map from the G to G. So the inverse exists. Okay, it's a one-to-one map.
Is it a linear map?
Huh?
Does it have to be a linear map? No.
Yeah, to have the vector space structure. Correct.
Correct.
Yeah. So this should also, sorry, I should have mentioned that, preserves the vector space structure. So phi of x plus, ax plus by is equal to a phi of x plus b phi of y. So the vector space structure must be also preserved. Both of these are the defining properties of the Lie algebra. So those are preserved. Okay, an example we have already seen. I think we have seen the adjoint action, right? We have seen the adjoint action where, so in that case, so for any G in the group, not in the Lie algebra, the group, there was a concept of adjoint action which was x goes to gx G inverse, right? Or G inverse xg, doesn't matter. That was an automorphism for every G, right? So, I mean, if such an automorphism exists, you would want your metric, whatever the notion of metric is, should have this symmetry, should be invariant under this automorphism. Right? And that is satisfied. That is satisfied, unfortunately, yeah, okay, that is satisfied. So the way you try to show is actually this is left as an exercise 11.3, you know, but maybe again some hint. So what we want to prove is that we want to prove that b of phi x with phi y for any x and y is the same as b of xy. Right? That's what you would want your, of course it's not necessary, but if you can find such a metric, it is nicer, right? Because it has it preserves the symmetries. No? So the metric between x, the b of this form, the Cartan-Killing form between x and y is the same as Cartan-Killing form between phi x and phi y. Okay? So x is mapped to, so the picture is something like this here. I have the vector space, x is here, y is here, let's say. So x is mapped to some phi of x, and y is mapped to phi of y. Then we are saying that if I compute the bxy here, that's the same as b of phi x phi y. So somehow the concept notion of distance or length is not changing. No? So that is a nice property. Now this is left as an exercise. It's 11.3 exercise. But I mean, the way to prove is like this. I mean, you start from the definition. Look at add phi of x acting on some element, arbitrary element z. I mean, there is a line. If you just go through the line between before 11.3, there is this hint given. So try to look at that hint and then try to prove that. If you have difficulty, then I can try this. Okay, maybe not today. Today will be busy going through a lot of homework which I have given. So, okay, think about it a little bit. Otherwise, I can explain that tomorrow. But for the moment, we'll just assume that this has been proven. Okay. Finally, what is the very important thing is that I mean, let's see. Okay, now the statements that I'm going to make here now will assume that B is non-degenerate. Okay, that this what we call Bij, which is this n cross n matrix, where n is a dimension of the Lie algebra. So n is a dimension in the Lie algebra. So this will be some n by n matrix. So this will be n by n matrix, right? And the statement is that we are assuming that dit B is not equal to 0. Determinant of this matrix, n by n matrix, is not 0, which means it's invertible. So B inverse exists. So in such cases, so I mean, look at the steps what we have done here. We have started with, before introducing Cartan's Cartan-Killing form, we already started with the Cartan subalgebra. Okay, so it is some Cartan subalgebra, let's say C. So the full dimension is G is dimension n, and Cartan subalgebra will be some dimension R. So I call it R. R will be less than, of course.
R for rank.
Huh?
R for rank.
R for rank, yeah. R for rank. R is the, yeah, this is rank. Okay. Now what we had was the roots, alphas, alpha i's that I was calling alpha I. What is it? This lives in the dual space. This belongs to C star. The dual space. The star is just a dual. I mean, it's not a complex conjugation. It's just a dual space. This is the dual space to C. Okay. And you all know the definitions of dual space, dual vector space. It is just the space of linear functions on C. Linear functions on C. So alpha is a function on this linear function on the C. Now, of course, so that means for every h, this is some number. This is some number for all h belonging to C.
Now, we remember that for SQ3 you said that alpha 1 if a times h1 plus b times h2 and x1 alpha 2, you have a real number. So in that sense, you have a dual space.
In that space, yeah, the dual space, exactly. Yeah, I mean, okay, that is, yeah, the dual space. I mean, it doesn't have to be real. I mean, you could have also thought of as a complex space, and then it should map to some numbers, either real or complex, depending on your space, right?
So there should be some definition of alpha as a function of h.
Yeah, it should be. It's a linear function. That is the important point. The C star, we are talking about linear functions, which means alpha of say h1, ah1, ah plus bh prime is the same as alpha of a alpha h plus b alpha h prime. There's a linearity is important. I mean, without this, you cannot say anything about the C star. If you don't have this linearity assumption, I mean, the definition should involve already linearity. Otherwise, if you allow quadratic or cubic polynomials and so on, then I mean, it won't be that case. The linearity is very crucial. Okay, but so this maps, right? But I mean, when you have such a situation, this all before introduced the notion of metric. This all. Now we have a notion of metric. And so furthermore, let's assume that the metric is non-degenerate, so that inverse exists. Then what we have, so I have two spaces here, C and C star, right? Now here, I have a notion of a distance or metric here, so Bij, let's say the metric here. Then we can translate this notion of metric here to a notion of appropriate notion of metric in this space. Okay? That is what happens. I mean, so for example, so what does it mean here? So suppose I choose a basis here. Again, in the Cartan subalgebra, I choose some basis. So it's not the full basis, but let's say Ti are the basis for the Cartan, for just the Cartan. So I goes from 1 to R. Not the full n. I'm just looking at the subalgebra. In that subalgebra, I choose a basis. Then any h I can write as hi ti, summed over. Okay. And let's suppose, so alpha, so this is going to be some linear function, this is a linear function. So alpha h will be some alpha I hi. Alpha I are some numbers. Right? It's a linear function. It's the most general linear function you can write down, with this being some numbers. Hi, so, okay. Where basically alpha I is nothing else but alpha of Ti. In this basis, alpha of Ti is what I call alpha I. Is some number. Now, you can use the Cartan killing form to give a unique map. I mean, if I have some alpha sitting here, I can uniquely define some element here. Okay? And that is what we call, let's give it a name. H, we denote it by H alpha, because obviously which element it is depends on alpha. Right? So I can give a unique map using the Cartan killing form, and that map is defined in the following way. That alpha h is nothing else but b evaluated between h alpha and h up to some number which is one just uses for some convenience. Some number, okay, a constant number. It does not depend on which h and which. It may depend on your Lie algebra, the G itself, which you're looking at. This is not important. I could have just set it to 1. It doesn't matter. But it just turns out that if you define this map by some suitable number, the various formulae become simpler. You know, instead of some horribly fractional numbers, you get integers if you put some suitable number here. Otherwise, you get all sorts of fractions floating around. So it's just for simplicity, it's not important. So this we can do here, and that can be done easily because after all, here we said this is alpha IHI, right? And here, again, if I choose this basis, those bases here, this will be some H alpha HI, say HI, H alpha J, Bij.
This map goes from C to C star or from C star to C?
Yeah, so the map is defined like this. Map is defined through this equation. Okay, so you have an alpha H. So what we are saying is that if I can find an H alpha, okay, which is in the C, This H alpha is in the C, Cartan subalgebra. If this is in the C, H of course is in the C. This is in C, and this is in C star. No? Okay. So what we are saying is, if this is a question mark now, if I can find an H alpha in C, this satisfies this equation. For all H, that's the important point. Not just for one H, but for all H. Okay. Then that gives you a map. I mean, so you started with an alpha, and we are finding an associated element of C. H alpha, right? Yeah.
Why does it have to be unique?
Sorry?
Why does it have to be unique? This map mapping between C and C star.
I mean, otherwise, then what will be the definition? I mean, okay, well, we'll find unique anyway. For the non-degenerate metric, yeah, we'll find it to be unique anyway. Yeah. I think that if they are not unique, probably what will happen, I'm not sure about it, but I think what will happen is that this B itself is degenerate in that case. It is not unique. But when the B is, so I should mention here, this point I should say, I already kind of have assumed something. Yeah. B's? It's not just that, but you see, I mean, we defined the B, initial B was for all X and Y, where X and Y belong to G, the full Lie algebra. Okay? But now we are talking about only the Cartan subalgebra. Okay? So it is basically just restricting the original B to the Cartan subalgebra. Okay? And another thing you notice that one should be able to also prove that B of H with the X, if it is not 0 for arbitrary H is in the Lie algebra, in the Cartan subalgebra, if it is not 0, so B with any X alpha is 0. That's what you can prove. Where alpha is not 0. Alpha is the non-zero root. You could prove that. It's maybe.
By doing this, what I'm doing is finding some dual partners for each H.
For
each alpha. Sorry.
For alpha. I'm finding the dual. Yeah. Dual space. I mean, these two spaces are same dimensionality, right? So basically, as a vector space, they are the isomorphic. Nothing big deal. But what is problem is that there is not a canonical map from here to there. Yeah? Now, using this B, we can give a canonical map. So it's like I don't know if you are familiar with the raising and lowering of the indices. Have you seen that in the right? I mean. In the relativity course or something, right? This is basically like raising or lowering indices. So you see in this notation I am putting in a lower index for alpha and upper index for H. So H alpha will come with the upper index. Yeah. I mean, in fact, you can see immediately, we have this equation here, and this should be true for every H, and that is immediately given by alpha I equal to H alpha J Bij, right? Which I can invert it to obtain what is H alpha J. H alpha J is simply Bji, which is the inverse of that. This is the inverse of that matrix, alpha I. So this is nothing else but raising and lowering. Thinking of this as a metric on the Cartan subalgebra. So for this, you see, you need to prove that somehow if I write the metric in this B in this basis, where I chose this basis, right? If I write the B in this basis, where here is Cartan, and here is all the X alphas, no? Alpha 1, alpha 2, etc. If I choose this basis, in this basis it should be block diagonal. I mean, here it should be 0, 0, here. These are actually all blocks. I mean, yeah, okay. Here there is something which we need to further study that. Here there is something, whatever. But the important point is that these are 0.
You can say that it is something like if you want to define distances in a Cauchy space. then you can do it by multiplying a contravariant and a covariant vector. If you don't use the metric at all, but when you use the metric, you can say that okay, all the vectors are just contravariant. I will just use multiply.
Precisely, that's exactly.
So now you are saying that if we have a contravariant, we want to find a corresponding covariance. That's why, but that's what you
Exactly. Yeah. So it's just So there is all as I said, this vector space. These are the same. Nothing. But now we are giving a specific map between that and this. So if you think of this as a lower index mapping into a high upper index by using this metric. Okay. Now if I have done that, then I can define the a metric in this space directly, right? Because I could just define the metric if I have alpha. I mean the alpha and beta two roots. So there are two roots here. So roots, alpha and beta are the roots. Then I can define an alpha times beta, alpha inner product of alpha with beta. Notation that we are using is we are using this notation, bra and ket. It's just an inner product between alpha and beta, which can be just expressed as alpha I, beta j times b ij. So Bij is the inverse. What did I do here? Yeah, so this inverse, upper index. So this way, you see, before introducing the metric, we just had this relation that this was a linear function, right? Okay, on this space. But now using the metric here, I can talk about a metric there. Okay, then define the inner product between the two roots. So maybe I can just try to complete this. So let's see how it works. So what we want to do is to look at both SU2 and SU3 examples to see what happens. But before that, is it clear to all of you that this must vanish? This off diagonal terms. This is the B. So this is something. This is something. But this off diagonal must vanish. If not, let me just go through that argument. So let's suppose I look at B of H. H is an arbitrary element of this Cartan subalgebra and some non-zero root. X alpha for some non-zero alpha. So I choose that. I want to compute that. Well, this is nothing else but trace add x, add h, add x alpha, by definition. So we want to again go through the same analysis. I write down this matrix add x alpha. I choose this basis because that's what I want to show. That in this basis, this part should be 0, right? That's what we want to show. So, so if I choose this basis, then what is going to be add x alpha acting on these vectors, on any one of them. Well, x alpha with any, say, x beta, if I look at the commutator, so I want to ask what happens if I apply this on x beta. Well, beta could be 0. If beta is 0, that's a Cartan subalgebra itself. But any eigenvalues b, beta, okay, then this will have, whatever it is, it will be something which has eigenvalue alpha plus beta. That we have seen already, because these eigenvalues are additive when I take the commutator, right? So this tells me that add x alpha maps x beta to x alpha plus beta. Okay. So it's so in particular, if I take this beta equal to 0, which is the Cartan, okay, then this will map to x alpha. Okay. No, sorry, beta is 0, so add x alpha will take you to add x alpha, right? So now what will happen if I apply now? So first I apply x alpha on add x alpha on x beta. It took you to x alpha plus beta. Okay. Now I apply add H on this result, right? That's what we have applied. First add X alpha, and now I apply add H on that. So what I'm going to get? I will get add. So this will be acting. This will be the same as add H, acting on X alpha plus beta, which is the same as H X alpha plus beta, which is going to be alpha some number times X alpha plus beta. So what we are seeing is that overall this combination add H times add X alpha has taken X beta to X alpha plus beta. Correct. This combination. So this is the product add H times add X alpha. This combination has taken you to that. So if alpha is not 0, there is no diagonal element here. Right? If alpha is not 0, take alpha is not 0, then surely beta is not equal to alpha plus beta. Okay. Then this product will have no diagonal term. Right? And since we are taking the trace only counts a diagonal term, right? So this will vanish. So this will vanish if alpha is not 0. Of course, if alpha is 0, then there is no contradiction. So therefore it means that the only way this can be non-zero is if X alpha itself, if alpha was 0, which means this itself is in the Cartan, right? So that is why only this may be non-zero, but this would be 0. I'm writing here the B. Okay. So therefore, now if I assume that the full B is non-degenerate, then clearly that implies also this must be non-degenerate. Because if I want to compute the determinant, since this is block diagonal, it will be determinant of this times determinant of that. So if any of these factors is 0, then it's degenerate, right? So that implies that this is non-degenerate, if we assume that the whole thing is non-degenerate. Right? And in those cases, you can find the inverse of this and write that. Right now, so let us just see how exactly it works. I will start. I will just work with the SU2 example is given here, but that is too simple. So let me just work with SU3, which is slightly more complicated. So we will look at. So we have our standard. The basis for the Cartan. We chose this basis. Cartan subalgebra in that case was 2-dimensional, SU3, and we chose H1 and H2, the two basis for the two of this Cartan subalgebra, and the roots. And remember that we had the roots alpha 1, alpha 2, and alpha 3, and the minuses of them. And this was given by, this was the exercise 8.4, which you had already done, I think, or you will do probably. This was the AH1 plus BH2, was 2A plus 2A minus B, right? And alpha 2 is AH1 plus BH2. Was equal to minus A plus 2B, and alpha 3, which was the sum of the two, alpha 1 plus alpha 2. We just sum that up, so it's A plus B. Right? This was the. Okay. So we first want to ask what is H alpha? H alpha 1, H alpha 2, H alpha 3. Right? So in particular, let's look at what is H alpha 1. And then you can do the same thing for alpha 2 and alpha 3. So the defining equation for this is alpha of k, alpha 1 of, for any k is k, for all k, let's see, it is equal to some number which depends on the group, and this is chosen for convenience. It has no particular significance. BH alpha 1, comma k. right? That's what, that is a defining equation. And by the way, the convenient number is for SUN. This convenient number is simply 1 over 2. So the C is simply, this C, don't confuse with this Cartan Sabadura. I don't know, maybe I should put here like, no, this is complex number. The capital C. This is small c. This is a number. So this SUN is taken to be 1 over 2. It's not important because you will see that in final, when we go through, develop this whole formalism, we'll see that only the ratios will appear. Okay, ratios of these things, this kinds of things. So that is constant, this will disappear. Because this doesn't depend on which element you're talking about. This depends on just the group that you are working with. So it's not important. Okay. So we want to, so this is a defining equation, right? So we want to find what is this. Alpha 1 is given here. So we want to find out what it is. So let's see, this should be for all k. But of course, since it's a linear, so it is sufficient to look at the basis, right? If I can satisfy this for k equal to h1 and h2, then that is it. There's no more information because anyway, both sides are linear. This side is and that side is both is linear in k. No? So let us just, so we have equations, two equations, alpha 1 acting on h1 equal to this number, whatever, Cg, let me just keep it as it is, b of h alpha 1 and h1, and alpha 1 of h2 equal to Cg b h alpha 1 h2. Right? So these are the two equations. And that should fix alpha. So to see this, we use this, remember that was the exercise, that b of hk, where h and k both are, h and k are in the Cartan, was nothing else but the sum over alpha I h, alpha I k, summed over all roots. All the roots. Delta is the symbol for roots, the set of roots. Delta is the set of non-zero roots. Okay. And then there's also a notation delta plus, but delta plus is the set of positive roots. This is the set of positive roots. So I can as well, since we know that for every alpha there is a minus alpha for SU3, I can already write it as 2, and then this is restricted to delta plus. So we'll use this formula to determine these things, and use this information which was from the already. So left hand side, you see alpha 1 h1. Alpha 1 h1 is simply 2, right? So this is 2.
Where are you going to determine the Cj or
Hey?
where are you going to determine? H alpha 1.
H alpha 1.
Ah, okay.
Cg is just a constant. I mean, that does not depend on the h's and so on.
Ah, okay. Fine.
Yeah, so we want to determine H alpha 1. Okay, and this is 2, and that is alpha 1 of minus h2 of h2 is minus 1, right? These are the left hand side we know. Now for the right hand side we use this equation. So what is going to be H alpha 1? After all, it's an element of the Cartan subalgebra, so I should be able to write it as a linear combination of the basis H1 and H2. So H alpha 1 will be some, I don't know, let's say A, no, let me not confuse with the A here, something else, some other symbol, X, let's say X H1 plus Y H2. Okay? Yeah? S1 and S2. Okay. Yeah, I mean, anything. Yeah. So if I can, so our aim is to determine X and Y, right? And we have two equations. So in principle, we should be able to determine, right? Given the fact that this is also non-degenerate, we should be able to determine this. So let's just work it out explicitly. So this formula, so let's say, so here, so what am I going to get from this side? So I will get here, okay, there is a CG, right here, CG, times X, let's look at the X term. So that is B of H1, right? So this will be X times B H1, plus Y times B H2, right? I just use the linearity of the thing. So now B H1 is 2 times, so what is B H1? It is 2 times alpha I H1, alpha I H1. So alpha I H1 square. Right? I mean, this is both H1. So it's alpha I H1 square. So we can just find it here. So this gives you, so this is the same as 2 times 2 square, so 4, right? For this I have to sum over all I, right? So I equal to 1, it gives you 2 square. For I equal to 2, you get a -1. That -1 square is +1, and for alpha, for I equal to 3, you get again +1. +1 square is again +1. So you get here 1. And so this is 12, right? And BH1, H2, and so you can show that BH2, H2 is also the same, 12 again, because that's just exchange of B. B and the numbers are the same distributed. You can show that the same. But the interesting thing is BH1, H2. So now you get 2 times, say, alpha 1 of H1 and alpha 1 of H2. Alpha 1 of H1 is 2, alpha 1 of H2 is -1, right? So the first term is 2 times -1. Right? The second term is now alpha 1 is -1, and so alpha 2 of H1 is -1, and alpha 2 of H2 is +2. So once again you get a -1 times +2, and the last one, both are 1, 1. So you get here +1, right? And just you're using this formula now, right? So we are looking at alpha I of H1 times alpha I of H2, and summed over I. So I have to sum over all these 3. So this becomes -4 plus 1, 3. So -3. So this is -6. Okay. So now we just plug that here. So this gives you CG times 12x minus 6y. Now, so that is one equation. So we need both these equations to determine these two numbers, right? So now let's look at the second equation. So this is going to be, this again CG, and now x b h1 h2 plus y b h2 h2. Okay. I can erase this part now. So this is what, again we use this thing. So this gives you CG times x, h1, h2 is a minus 6x, okay, plus 12y, right? Is it 12? Yeah. Y this times 12. Okay. So that's the two equations, and so we have this here. So you see that if I now look at this equation, if I, for example, if I want to determine y, what I can do, I can multiply this equation by 2 and add, then x disappears. So if I multiply this equation by 2 and add, this gives you 0. So this implies y is 0. Okay. And then you determine x. For example, I can use this equation. So 12x, so x equal to, and x equal to 2 divided by 12 CG, which means 1 over 6 CG. Okay. And in fact, you see that I told you the CG is convenient to use this definition, because this is exactly for n equal to 3 is 1 over 6. Okay. So if you use that definition, it's just 1. Okay. That's for just for convenience. Otherwise, you will have this. Suppose I have chosen CG equal to 1. You're going to have this fractional numbers floating around everywhere in all your formulae. But if you choose this universally for SU3, right? Then this fractional, a lot of these fractional numbers don't appear.
Is it also convenient in F2N groups? We saw that it is convenient in SU3, but if you do conversion for SU4 or 5, is it still convenient?
Yeah, it's convenient. Yeah. Okay. And similarly, you can show. So the conclusion is, therefore, the H alpha is simply, if I choose the CG equal to 1, so H alpha 1 is simply H1. Okay, if CG was 1, it would be 1/6, but it's some number times H1. No? With this choice of CG, with that choice of CG, it is simply H1. You go through the same analysis now, but we also want for alpha 2, right? So you'll get similar equations for alpha 2, right? Alpha 2 acting on H1 is some number, alpha 2 acting on H2 is some, and then you'll find, and that's I think is an exercise. I think, yeah, that's exercise 11.4. You will show that can show that H alpha 2 is also H2. That's nice about it. Okay, so what we have done here is that this way we have given a map from alpha to H alpha, and we are finding that map is actually a very simple map. So alpha 1 is mapped to H1, and alpha 2 is mapped to H2. Right? But now you can ask what is the okay, I have another. Let me just do the last bit, and then I'll stop. Now, as I told you that, given this, I can also introduce a metric inside in the roots, among the roots itself, inner product among the roots itself, right? And that is given by that. This is of course written in the kind of basis where I'm choosing a basis, writing the B in terms of the indices and so on and so forth. But you can write this equation in an invariant way, and the invariant way is simply the statement that alpha beta. So you define this alpha beta is equal to simply this equation, again the same CG times B of H alpha H beta. Okay. So you see this equation, we use this equation to determine what is H alpha and H beta, and that is uniquely determined if B is invertible. If B is not invertible, what will happen is that you will not be able to uniquely solve this equation, these two set of equations. Okay. But it's precisely because it's invertible that you can invert it and get unique solution. So then you define, this is your definition, that the inner product between the roots themselves is given by the Cartan killing form between H alpha and H beta. Okay. That's so we can, now that we know what is H1 and H2, we can determine. So we can determine all the metric. So for example, alpha 1 with alpha 1 is the same as CG times B of H1 H1, right? Because H alpha 1 was nothing else but H1, and that we already calculated, no? B H1 H1 was 12, no? So this is 12. So this is CG times 12. Okay, which if I use the 1/6, then this is the same as 2. Alpha 1, alpha 2 with alpha 2 also for the same reason, is the same as CG B H2 H2. And this is again 12, so 12 CG, which is equal to 2 for that choice. And finally, alpha 1, alpha 2 is CG B H1 H2. H1 HB, H1 H2 you calculate it will be -6, right? So it's -6 CG which is equal to minus 1.
What about the alpha 3?
You can also do for alpha 3, but that just comes from the, again, alpha 3, let's do that, good point. This map is linear map, right? From alpha to BH is a linear map. So since alpha 3 is simply alpha 1 plus alpha 2, okay, so H alpha 3 is going to be H alpha 1 plus H alpha 2, which is H1 plus H2. Okay, so we can also do this for alpha 3 then. So let's see, again alpha 3 with alpha 3 will be CG of B H1 plus H2, because H3 is, we saw H3 is H1 plus H2, H1 plus H2, sorry, H2. Now what is this? This is CG, so B H1 is 12, right? B H2 is also 12. Then you have B H1 H2, you open it up, so linear, right? Bilinear, I mean linear in this, linear in that. So H1 with H2, that is minus 6, and H2 with H1 is again minus 6, so which is again 12 CG, which is equal to 2, if CG is 1 over 6. And again you can check alpha 3 with alpha 1. Alpha 3 with alpha 1 is CG B H1 plus H2, comma H1, which is CG times 12 minus 6, so it is 6 is 1, I mean 6 CG, which is 1. And finally alpha 3 with alpha 2, this is the last one, right? And you can see that this time H1 plus H2 comma H2, which will again give you the same number, right? So it's again 1. And this is exactly the picture we had in the root space, right? I mean the roots that you were drawing was exactly this, right? You see that, so we are saying that something, if you think of this is like length square of alpha 1, this is length square of alpha 2, length square of alpha 3, etc. So length square are 2, so that means length is square root of 2. Okay? And this one, the alpha 1 with alpha 2 is giving you minus 1. That means the angle between them is 120 degrees, right? So the picture is exactly this coming out, right? You have alpha 1 here and alpha 2, same length, but angle is 120. And alpha 3 is also same length, but dot product of alpha 3 with alpha 1 is plus 1, not minus 1. So it's 60 degrees. I mean alpha 3 dot product, both alpha 1 and alpha 2 is 1, 1. So 60 degrees with alpha 1 and alpha 2. So that's this. So it is 60 degrees. So this you see that the metric that we are getting for the roots, it's and you see this is all basis independent. I'm not choosing any particular basis, whether it's not an issue of H1 or Y. We are using sometimes H1 or Y. It's completely basis independent.
So you have not defined any coordinates.
Exactly. Yeah.
Completely defined.
Yeah. So
Here to find the angles, we are divided by 2.
repeat that again, sorry.
To define to draw the angles, we are divided by 2. Because the scalar product is 1, so it should be 90, 100.
I mean, so the length is root 2, right? We said from this length is root 2 for both alpha 1 and alpha 2. So if I take the dot product, think in terms of some vector, alpha 1 dot alpha 2, two-dimensional vector, no? These are all in two-dimensional plane. This will be the length of alpha 1, length of alpha 2 times cosine of the angle between the two, right? Now this is root 2, so 2 cosine theta, and that is minus 1, so that is why theta is 120 degrees. And in this case it is 1, so it is 2 cosine theta is 1, so cos theta is half, which makes it 60 degrees. So this is the way you get. Okay. Now, I mean, the only thing is that what happens if I had chosen other basis, h1 and y, no, or lambda 8, lambda 3 and lambda 8, that basis, instead of this basis. See, in this basis, bh1, h2 is not 0. bh1, h1, I mean, this number, I just erased it. bh1, h2 was minus 6, right? So this means that they are not orthogonal. h1 and h2 are not orthogonal. If you had used instead what we are calling lambda 3, which was basically something like proportional to h1 plus h2, right? No, h1 minus h2. I mean, lambda 8, sorry, lambda 8 was 1, 1, minus 2 up to some number, root 3, right? And h1 is 1, minus 1, 0. h2 was 0, 1, minus 1. So I need to take what I should do to get 1, 1. I should take this plus 2 times that. Huh? So if I take h1 plus 2h2, then this becomes 1, 1. And then here you have minus 2, which is exactly the thing. Then root 3. Okay, root 3 is not important. Let's say root 3 then, right? 1 over root 3. That will be your lambda 8. But then you see h1 plus h2 is orthogonal to h1. From this formula you can see the b of h1 plus 2h2 is orthogonal to h1. Because h1 with h1 is 12, 2h2 with h1 is, h2 with h1 is minus 6, so this becomes minus 12. So it's orthogonal. So that just becomes convenient. And with this 1 over root 3, what will happen is that if I have chosen this basis of lambda 3 and lambda 8 as my basis, then the metric, the bij, is simply delta ij, proportional to delta ij. That's all. It's a convenient basis, but I mean it's not needed to, because this definition is quite intrinsic definition. You don't need to choose any basis. You know, this map. What we are doing is this map is very intrinsic. Here there's no question of choice of basis here. No? So these statements are completely basis independent.
If we take the Cartan-Filling form of one page, it can be anything, not necessarily H. For example, you have X, any element of the algebra. So if you take the Cartan-Filling form of X with itself, can it be negative?
X alpha with itself, that will be 0.
X can be any, it will be 0.
Yeah, because remember that thing that we said, X.
No, X is not in the. I'm not making the that someone or something that is Cartan and something that not.
No. Yeah, sure. Understand. Actually, just since you raised this point, let me just continue that. That statement is much more general than what I did. What I did was to just show that B of between H and any X alpha is 0 if alpha is not 0. Right?
No, I'm not talking about SQ2. I'm talking about generally.
Yeah, generally algebra. Generally algebra. Right?
Okay.
This discussion was for generally algebra.
Okay, so it is always 0.
Yeah. How did we show it? We said that okay, for this I need to look at the trace of adh. Okay, so first let's look at the adh times add x alpha. Okay, and this is acting on. So I choose some basis where here, I mean whatever it is. Suppose it acts on some x gamma. This gamma could be 0 or not 0, whatever. 0 would mean that it will be in the Cartan. First of all, this already tells me that this guy is going to be something in alpha plus gamma, because additive, because it's a commutator of x alpha with x gamma. So whatever it is going to be some with eigenvalue alpha plus gamma.
No, I'm saying that suppose that you have some x alpha, and you take the Cartan-Filling form with itself, x alpha, can it be negative?
This is what I'm trying to say. Just 1 second. That will be 0 automatically, because now let's take add of something else. I mean anything else. So choose some x beta. Beta could be 0. Beta is 0 then. So add x beta. So already this acting on that gives you alpha plus gamma. Now I'm looking at add x beta acting on this. That will give me x alpha plus beta plus gamma. Right? So And now I want to take the trace. So the combination of these two took x gamma to x of alpha plus beta plus gamma. And now I have to take the trace. So the trace will be non-zero only if alpha plus beta is 0.
Yeah.
You see? So for the trace to be non-zero, for the trace to be non-zero, alpha plus beta must be equal to 0. If alpha plus beta is not 0, it's completely off-diagonal matrix. I mean, this product of these two matrices is completely off-diagonal. So trace is 0.
It means that if I take the Cartan filling form of a Cartan with a Cartan, it would be non-zero.
It will be non-zero, yeah. Okay, that's if the metric is non-degenerate.
Yeah.
Yeah. Okay. I mean, the next time we'll study this. We'll properly define what we mean by semi-simple algebras and so on. No. So there, it will turn out, which we will not prove. I will just assume that if there is an algebra which has no ideal, no invariant subalgebra, no invariant abelian subalgebra. Like for example, the Poincare case, ideal was a translation. Translation was abelian, right? So if there's the algebra has no abelian ideals, then the Cartan killing form is non-degenerate, and vice versa actually. But we will not prove that. So I will state some theorems because then that will take us to prove it will take some time. Because in general, although intuitively one can see it. But notice that also this, since you raise this question, so we are saying that if alpha plus beta is not 0, then that metric is 0, right? And this will be 0. Now suppose I have a root x alpha. I have a non-zero root alpha not equal to 0, and I found something, some eigenfunction. You see, so far both in SU2 and SU3 you saw that for every alpha there was a minus alpha, right? But then you can ask, maybe it's just an accident that in SU2 and SU3 it happened to be like that. How do we know that for everything, for other algebras is that? But this means, if we demand that the B is non-degenerate, okay? Now that implies that there should be a minus alpha also. Because otherwise x, if minus alpha did not exist, right? Then x alpha with anything is 0. Then the metric will be degenerate, right? So if I'm focusing on the semi-simple algebras, where the metric is by definition not degenerate, then it is guaranteed that there must be a minus alpha. These are the kind of arguments we'll be now using. Every step we'll be using similar arguments. So everywhere this non-degeneracy of the B will play an important role. And that will allow us to completely classify all the possible simple algebras.
Only simple, not semi-simple?
Semi-simple, we'll see that semi-simple is just a direct sum of simple algebra. So if you know properties of simple algebras, you know the semi-simple algebra. Okay, so see you tomorrow. Nice job. Nice flashing still. How come?